Today we're going to look at the powers of complex numbers, and we're going to build on what we did in the previous lesson where we multiplied complex numbers together. Now, I don't pronounce this, probably don't pronounce this well, but this is DeMoivre's theorem, and we are going to look at how this is developed. So we're going to start off with this guy, this polar form of a complex number. We have our modulus and we have our arguments, and here we're going to square it. Well, you know, squaring it is the same as writing it twice and multiplying it out. So that's what we're going to do, and we're going to take a look at it. So here we've written it twice, and we're going to use what we did yesterday, multiplying two complex numbers together. We multiply the moduli, which is r times r, so that's going to give us r squared, and then we add the arguments. I have a theta and a theta. So this ends up being r squared times the quantity of the cosine of 2 theta plus I times the sine of 2 theta. So when I square the complex number in polar form, I end up squaring the modulus, and then I'm multiplying the argument by 2. So now let's look at what happens when I cube this complex number. Well, I've already squared it, so cubing the complex number is the same as multiplying one of these by the squared term. So we have r squared, this is our previous answer, and to that I'm going to multiply one more of the original. So we use the same rules. We multiply the moduli, and that's going to give me r cubed, and we add the arguments. So I have a 2 theta plus a theta. That's going to give me 3 theta, and hopefully you will start to see the pattern here. We have the cosine of 3 theta plus I times the sine of 3 theta. And so you should start to see a pattern. So given that, what do you think the r cosine theta plus I sine of theta raised to the 4th power would look like? And hopefully you're starting to recognize that it would probably be raising the modulus to the 4th power and multiplying the argument by 4. So this is a really easy way to raise complex numbers to an exponent. Otherwise, we would have to use the binomial theorem, and Lord knows I know y'all would not like to use the binomial theorem if we don't have to. So this is a much easier way to do it. To generalize this, the generalization of this process is called, and I don't pronounce it well, DeMoivre's theorem. And so here it is. It says that when I take the polar form of a complex number, so we'll write it here, the cosine of theta plus I times the sine of theta, and I raise that to any exponent n, that's equivalent to raising the modulus by that exponent and multiplying the argument by that exponent. So I have n theta plus I times the sine of n theta. So I can raise a complex number to an exponent in one step. Think about that. If n were some disgustingly large number like 20, all I have to do is take the modulus and raise it to the 20th power and multiply the argument by 20, and then do some simplification, probably find the angle that's coterminal to it or whatever. But that's tons easier than going through the binomial theorem to do that. So this is a handy thing that we want to make sure we understand. Alright, again, we're going to use this theorem to find the powers of complex numbers. So here I have 1 minus I raised to the 8th power. You could treat this like a binomial and expand it with the binomial theorem, or you could convert to polar form and then use DeMoivre's theorem, which is much easier. And that's what we're going to do. So let's convert this to polar form. If I sketch a graph, I have and positive 1 on the real, negative 1 on the imaginary. So I'm down here, and my radius is going to end up being radical 2 because this is a 1 and a negative 1. But you could go through and use Pythagorean theorem. Your radius ends up being radical 2, and your angle is going to be the inverse tangent, and it's a fourth quadrant angle, so we're okay, of negative 1 over 1, and that's going to be negative pi over 4. So I have my original number here. I have 1 minus I to the 8th power, or just the original one. Well, we'll do it this way. That's going to be equal to radical 2 times the cosine of, instead of writing the negatives, I'm going to change that to 7 pi over 4. It's coterminal with it, plus I times the sine of 7 pi over 4. And all of that raised to the 8th power. So now I'm going to apply DeMoivre's theorem to finish this up in like one step and then a step to simplify. So it just takes 2 steps to do this. I'm going to take the radical 2 and I raise it to the 8th power. And then I take the cosine and I multiply my argument by 8. And that's what this looks like. So in the end, if I take radical 2 and I raise it to the 8th power, I'm going to get 16. And then if I multiply through and simplify my fraction here, I'm going to get 14 pi. So the cosine of 14 pi plus I times the sine of 14 pi. I could take it one more step and find the angle coterminal to 14 pi. That's going to be 2 pi. If I want my angles between 0 and 2 pi inclusive, it would be 2 pi. So I could write it like this, depending on what's required. So this is much easier than trying to use the binomial theorem and expanding this to the 8th level. This theorem works for any exponent, any rational exponent. So we can also use it to find the principal roots. If I want to find the principal root of radical I, it looks kind of weird, the square root of I. We're going to rewrite it. That's the same as my real part is 0, my imaginary part is 1, and the entire thing is raised to the 1/2 power. That's how you have to look at this, because this can be written out as the real part and the imaginary part, and that's all the radical is the 1/2 power. So we're going to write this in polar form and then use 1/2 as our exponent. 0 plus I, that means this is the real, this is the imaginary. I'm completely on the imaginary axis. So that means I have a radius of 1, and my angle is going to be, my argument is going to be pi over 2. So a lot of times you don't have to go through the formulas. If you can graph the point, you can figure out the radius or the modulus in the argument. So now what that means is I'm going to raise 1 to the 1/2 power, and I have the cosine of 1/2 times pi over 2 plus I times the sine of 1/2 times pi over 2. And that's all you got to do. So the square root of 1 is 1. He's an implied 1. I'll write it for now. And this is cosine of pi over 4 plus I times the sine of pi over 4. Now remember, just to finish this up, if you ever want to determine the rectangular coordinates, all you have to do is process this out. Find the exact value of the cosine of pi over 4 and the sine of pi over 4. Since my modulus is 1, I'm basically distributing a 1 in this problem. So in rectangular form, this is going to be the cosine of pi over 4 is radical 2 over 2 plus radical 2 over 2I. That's what you get. So we can apply this theorem to any exponent, whole numbers or rational numbers. And Again, it's much easier than trying to raise a power or take the square root in rectangular form.